My research field is speech translation, which is the task of translating from speech in one language to text in another language. There is also some research from speech to speech. This is quite new. And I also collaborate, well, I'm part of the machine translation group in UPC. So that's, yeah, the main topic of research in our group. And they also collaborate with the image processing group in UPC, where they are trying also to do sign language translation. But in general, as you may realize, my whole research field is around machine translation, whether coming from speech or sign language or typical machine translation coming from text. You will see today that I will speak a lot about machine translation because this is kind of the field where the transformer was proposed by the first time, for the first time. However, the idea, I mean, I understand that there's no one here working on this topic. The idea is to show you how the transformer works, to get you, to show you this knowledge about these parts of the transformer that you may apply in your own research. See if this works. It's not working. Why?
Some delays.
Okay. Yeah. Before starting, some acknowledgements of people that collaborated in the creation of these slides. Gabi, who did a lot of classes in the UPC, in the UPC school also, and postgraduate course that we have there. Marta, my supervisor, who is now at Meta, and other like Carlos, who is a colleague of mine from the group, Amaya and Santi, that also at some point taught this class, and we started iterating these slides. So today's presentation, the title is The Transformer Revolution, and you may be wondering, why do we speak about the revolution? Yeah, I just wanted to make a joke with these stable diffusion models that we have nowadays, that we can just generate an image from text, just from something like a war with transformers and a revolution, and I generated these images. So obviously, we're not talking about the revolution. We are talking about something super interesting as this. This paper is the revolution, okay? And yeah, this is not so nice, right? I don't know. It's kind of, it may be more interesting this, but yeah, I promise you that what we have here is super interesting, and this is what we will cover today. So what we have behind this paper is this architecture that we have here. I will try if this works. Yes. So this is the main figure of the transformer paper, okay? And this depicts the transformer architecture. By the way, I didn't mention, I'm assuming that you have some basic knowledge, at least, about neural networks. The ones that have a deep knowledge of neural networks, you can interrupt me to get as many details as you need. The ones that never heard about neural networks and have a very basic knowledge, just try to get the general ideas, okay? Like how these mechanisms that we will present today work. But yeah, interrupt me as much as you need. That's another thing that I wanted to say. Like, I like interactive presentations. So yeah, we are here. This is the transformer architecture. And why we talk about the revolution then, because these lead to all these, like among others, okay, all these advancements in technology. For example, we have GitHub Copilot, which is probably the example that you've probably heard about. It's this code completion service that GitHub has. So we will see today how it works internally. That at the end, this is a transformer decoder, and we will understand how it's working. And we will see other examples. Probably you've heard about AlphaFold. This is moving, right? It's not me.
Yeah, okay. Yeah. This one is a bit.
Okay, I will go there then. You probably heard about AlphaFold, which is this picture we have here. Or maybe some of you have heard about large language models like GPT-3. It's this field that we have here that we will see more later. So when we talk about the revolution, we talk about, yeah, a single architecture proposed in this paper that lead to all this new field of research. So this is the paper again, and I don't know if there is something that you find interesting from this. The title? Who said it?
I said.
Okay. What is the title saying? Attention is all you need.
That's right.
Okay. So yeah, this is a quite catchy title that they choose. So the first question is, okay, what is attention? If it's all we need, we need to understand what is attention. Anyone has heard about the attention mechanism? Okay, cool. I will now talk about attention, okay, for the ones that never heard about it. So I will present the attention mechanism, which is a key part of the transformer. But first, I have to talk also about sequence-to-sequence models, okay? Then once I have presented the sequence-to-sequence models and the attention mechanism, I will present the transformer architecture. We will go deep into the details on how the transformer is, what are the parts of the transformer. And until this point, I will be talking a lot about machine translation, as I told you. At this point, we will see that we can go away from machine translation, that this can be applied also to many natural language processing fields or tasks. And we will close with the last section where we will see like some real world cases, or like that we can go beyond even processing text, and basically that we can find transformers every day nowadays. Okay. So let's start with sequence to sequence. And before going to the sequence to sequence architecture, we have to understand this encoder decoder architecture. So the encoder decoder architectures are these kind of neural networks composed of two submodules, where we have we have some data at the input, we encode it, we get a representation normally in a lower dimensional space, and then we can use this representation to feed a decoder and generate another output. This could be, for example, and this is something really general, like a really general structure that is applied in many research fields. For example, if you want to, I don't know, do image segmentation, you have an image at the input and then get the contours of which are the objects that appear in the image. You can use an encoder decoder architecture where you have an encoder that gets a representation from the input image, and then a decoder that generates these masks to do the segmentation. This is an example of general encoder decoder architecture. But then in the particular case where we have a sequence and the input, and a sequence and the output, this is what we call a sequence-to-sequence model, and again is composed of an encoder and a decoder. Okay, the idea here is that, general idea, we will end up in machine translation, but we have a sequence at the input and we want to transform it somehow. So what we do is we encode it, we get we get now here a context vector, which is this representation, and then we feed the decoder to generate the other sequence. And this way we are transforming from one sequence to the other sequence. As I was saying, this can be applied to machine translation. Okay, this is my favorite task, you will realize today. And in this case, what we have is a sentence in French at the input, je suis étudiant. I generate a context vector, and then I use the decoder to generate the translation. I am a student. Okay. So this is basic sequence to sequence for machine translation. More concretely, what we have inside the encoder to do this task is this encoder RNN and decoder RNN, where we process every word at a time, and we end up with the representation, we feed the decoder, and we start generating words. Okay. By the way, no, I will tell you later. The thing is, now I told you we have something called encoder RNN and decoder RNN. And for some of you that haven't heard about it, we need to stop now, do a parenthesis, and understand what an RNN is. Okay.
Just 1 second.
Yeah.
So the input of the second stage of encoding is the already coded output of the first one, and then the natural word of it. Interesting.
Yeah, exactly. And it's super nice that you interrupted me here, because I wanted to give you an analogy that I was forgetting to give you. The idea here is kind of, I like to understand it as a person reading a sentence, then getting the concept of what is being said, and then start writing the translation. It's somehow what we are doing here. So we feed all the words sequentially here, and we get the representation that it can be understood as this idea that we have in our minds of the meaning of the sentence. So in a mathematical way, by a single vector, we collapse there all the information of the input sentence. Okay? And we use that then to start writing word by word the translated sentence. I don't know if this analogy. Yeah.
The context is retaining the memory about the past sentence.
Exactly.
Seen somehow, as you said, in a condensed way.
Yeah, yeah. So that's what we are doing here. Any more questions regarding this? Yeah.
So the number of blocks that you need actually depends on the length of the sentence, original and translated. So how can you?
Okay. The thing is now we have to talk about RNNs.
Exactly.
We have to talk about RNNs. Okay. So RNNs are these special kind of neural networks that have memory. And how do they incorporate memory? So imagine, let's put another example here. Imagine that you are processing weather data. Okay, imagine that you have a weather station and you record every 5 minutes. You record the temperature and the humidity. Okay, and you want to do some kind of sequence modeling in this. So what you would have is in the input of the network, you can have the temperature and the humidity measurements. Okay, but with a normal MLP, multi-layer perceptron, you can just mix information from these two features. Well, we have 3 here. Anyone knows something about weather? We can have temperature, humidity, and I don't know, something else. Precipitation, or I don't know. Pressure, right. So we have these 3 features here, and we can process them. But we want to do sequence modeling. So we want to take into account the previous, like what was the weather before, okay? Because maybe we want to do forecast. I don't know, some general concept here. So if we incorporate this recurrent layer here, what we are doing is that we are not just considering the current features that we are measuring, but we also, this arrow is the key part here. So it's considering also the previous outputs of that layer. So this way we can model time. This way we are also considering the measurements of temperature, humidity, and pressure that we had in the previous time steps. So this is the key that it's adding this memory. So going more into details on this, I mean, this is not the objective of today's session, but I think it's interesting for you to understand how RNNs work to let me explain you about attention. So we have these 2 matrices here, which are the keys to understand RNNs. So the W matrix is what we can understand as feed-forward weights. So these are basically projecting the features that we have at that current time step. So we basically mix information coming from temperature, humidity, and pressure. But then, thanks to this U matrix that we have here, that is the one connecting the output of this layer to the input again. This is the recurrent weights. So this is where the time is processed. Okay. So somehow we can understand the W matrix as a projection in the features dimension. This is something I like to explain this way. So we have this features dimension, and we have another projection in the time dimension. Okay. Any question till this point? So answering before's question, now what we have here is that we don't. I go back. So in these encoders that we had here, it's not that we have to define a specific cell for each word. So it's not depending on the sequence length. It's basically the same one that every time that I feed a new word, it's considering all the ones that have seen before, because we have this recurrence, we have this memory. So when we arrive at this point, this representation has seen all the words in the sentence. Okay. So we've seen this kind of representation till now about RNNs, but this is not the way we normally represent RNNs, and this is something that it's also important to understand later the transformer. We normally unfold this representation. So as we were doing before, well, I don't want to distract now. So here in the horizontal axis, we have the feeders. So in the example we were saying before, in the horizontal axis, here we have the temperature, the humidity, and the pressure. And then I like to imagine in the depth dimension the time, so that the multiple time steps that we process are somehow in the depth. So when we unfold it, we are doing like a 90 degrees rotation here. And what we have now is that in the horizontal axis, we have the time. So we can see the sequence now in the horizontal axis. And what we had as feeders, I like to imagine them as a depth dimension now. So each one of these circles here represent the vector with the temperature, humidity, and pressure. And then each one of them is a different time step. So remember, I told you that I was picking these weather measurements every 5 minutes. So what I will have here is these measurements at every 5 minutes. So this way, with a view matrix that now we see this way, I can model sequences. Okay, and this is mainly what we are doing in the previous encoder architecture. But if we make it a bit more complex, we can stack multiple layers of this one. Then we build a recurrent neural network. So an RNN basically is a stack of recurrent layers. And this allows, again, this is the unfolded view. So these are different time steps. The thing is that this output that we have here has information of all the inputs that we have before. Okay, this collapses information of everything. And this, well, before transformers, the model that we were using were LSTMs. I don't know if you heard about LSTMs. So it's kind of an evolution of the vanilla RNNs that I've just presented. So this would be the equivalent operation for a vanilla RNN, and it got way more complex with LSTMs. So again, it's not the goal of the session, but just some background on how LSTMs work. Basically, they added this arrow here, which is called cell state, and basically this is a long-term memory. So instead of just keeping, I mean, this idea of reading the sequence and collecting information from the inputs, now we have a mechanism where we can store long-term memory, and thanks to some gating mechanisms that I won't enter into details today. We can just, the network learns how to forget information from the long-term memory and how to add new one. So we can maintain this long-term memory separate. And here I have some other figures about this LSTM, but again, it's not the goal. Okay, so yeah.
Once the information is forgotten, it's not possible to recover it, right?
Yeah, exactly. The cool thing is that the cool thing about LSTMs is that, yeah, they have these gates that can control this. So these are shared, these are learned projections that learn how to forget and how to incorporate information to this long-term memory. While before, I don't know if you realize, maybe it's a bit complex now and we don't have to enter into details, but we just have this matrix here to model things in time. It's way more easy with RNNs to forget about things that the network has seen. We have now a controlled way to keep information, to store separate information, and at every time step to choose what to remove and what to.
May I add something?
Yeah.
Technically speaking, the matrix view is sharing weights full time, okay? Because we are using the same matrix full time to propagate information. Okay? You can see it there in the previous slide. If you have the matrix view, which is being shared in use at every time step. So this is time sharing of the weight of the neuron.
It's always the same.
This is a problem. Why? Because they have found that when you propagate the information back to train the network through back propagation, which is the standard way of training a neural network, this sharing creates a problem which depends on the eigenvectors, eigenvalues of the network. And oftentimes, the gradient that we propagate back to train the network, they get killed. So, and you get into this vanishing gradient problem because of the shape of this matrix that is not under your control. So to get around this problem, they created the structure that you see here, which is much more complicated, which is not the topic of today's talk, but it is, I believe, one of the main reasons why they need to go to this complexity. Okay. With this additional control, they can also avoid the fact that the gradient, when you train the network, will be killed. Okay. Sorry.
No, it was totally nice. So we are now prepared to go back to this figure, we already saw this one, but we didn't know what RNNs are. So we close the parentheses. Is there a question? Okay. Okay. We now understand what we are talking about when we say encoder RNN and decoder RNN. Okay. Just now I want to clarify here. You can see that we are putting words into the network. So obviously we cannot put words by themselves. Just for today's session, just assume that we have a way to represent words as vectors. So we have a vector representation for each word, which is different for each word. That's all. Okay. For today's session, I think it's enough. So we are inputting here vector representing the word student, and yeah, now here we can generate the translation. Yeah, here we have again another representation of this idea. So here we have the encoder RNN. These are the hidden states that I'm computing. I mean, these hidden states in the recurrent layers that I obtain when I start passing different words, and when I arrive to the end of the sentence, I can use this to feed the decoder. And as you see here, we have a begin of sentence token. This is something that we use to start the decoding, and then conditioning this first cell of the RNN with the hidden state coming from the encoder, I can generate the first word. Once I generate the first word, I put it to the input, and again with this hidden state and this input, I can generate the next word. So this is something that we will be seeing in the transformer also. So this idea of the idea of the decoder is to predict the next word for always predicting the next word. Okay. But in general, the idea is that we do the prediction of the next word by conditioning it with some representation coming from the encoder. Any question till this point?
Yeah.
Yeah.
Do you pass to the decoder just the last stage of the encoder?
Yeah. So I ask you problems with this architecture.
Again?
I ask you problems with this architecture.
Yeah, probably you only have one input and you have to generate sequence of words without. Well, it depends on the starting, right? On the seed that you.
This?
That's right.
No, that's not the main problem we have here. So you're saying I passed just the last one. And the thing is that it sounds beautiful, right? What I told you before about reading the whole sentence, then I get the idea, and this is a vector that collects all the information of the input sentence, and then I use it to generate the output. This sounds beautiful, but
doesn't work.
Come on, we cannot put the meaning of a whole sentence in a single vector. And the first reason, and the most easy one, is I can have different lengths. So imagine I have a sentence of 4 words. It's okay. Maybe the vector can collapse the information for this. Imagine you have a super long sentence. These people that write without commas or points, you have a sentence that is a paragraph and you want to translate it. How can you collapse all that information? Imagine again what I was telling you before, no? If I read the sentence and I read it, I forget about the sentence, I just have the idea in my mind and then start translating. I can do it for short sentences, but imagine with a really long sentence, I will have to look back again and see exactly which were the contents to do the translation, right? So this
problem. So how do you know when to stop the coding?
Good question. So the same way we have here the begin of sentence token, we have another special token, which is the end of sentence token. So when the decoder generates an end of sentence token, it's kind of saying, okay, I'm done. This is the end. So in general, the thing is that this represents a huge bottleneck for training these systems, okay? Trying to collapse everything into a single vector, and then from this vector, trying to generate the output. Any questions about this? So I like to start giving you the intuition of attention, okay? And imagine we have I don't know if you see it properly. So we are translating from English to French. We have this sentence: the agreement on the European Economic Area was signed in August 1992. And we want to translate it to French. If we were doing what I just showed you, we have to process all this sentence through an RNN. And then we use the representation we get here at the end to feed the decoder and start generating words. So to generate the word European, which is directly related to European in the input, I have to follow all this path. So the representation, I mean, the hidden state I get here in the European, I pass it through the RNN. It can be whether a vanilla RNN or an LSTM, but I have to pass through all these words, then pass this information through all these words. And then when I have here, then the RNN will be prepared to say, okay, that information at some point you kept here, then you have to use it now. And this is not intuitive because this information here is really in a really specific location at the input. So there is a clear connection between the generation of this word and this word at the input. I don't know if you see this intuition here. Mm-hmm. It doesn't make sense to keep all this information all this way to arrive till this point. Doesn't make sense. You should have a direct connection for this. I also like this example, but it's not seen properly actually. So when we are generating, this is a bit more complex one, but it's also the same idea. We want to generate la, the article in French, and the main information comes from the in the input. But here in this case, it's a bit more difficult because the doesn't have gender information. So it's not clearly seen, but it's also picking information from area, okay, which carries the gender to be able to generate the word la in French. So again, here we have an example of information that comes from a very specific places, from the and from area, to be able to generate la, okay? And if you're tired about machine translation, I also have an example of another task, which is speech recognition. So we can also do speech recognition with an encoder-decoder detector, with a sequence-to-sequence model. And again, what we would have at the input is the spectrogram, and at the output in speech recognition, we normally work with characters instead of words. So imagine again, no, to generate this character here, all the path that it should have been done in the typical sequence-to-sequence model. While this is directly connected to a very specific region in the input spectrogram. Even in this case, it's even more dramatic because sequences, spectrograms are longer than sentences with words. So we have a longer sequence here, and we are processing with characters, which leads with a longer sequence. So the path that should be done here to carry all this information till this point, it's even longer. So it's more prone to forget about this. Okay. So this was the intuition to arrive to the attention mechanism. Any questions? Please ask. Yeah.
There's no need maybe to get into the details of the word. It's supposed to be discrete, isn't it? So I'm just wondering the end token. When you say it's used as an end token, looks like something discrete that's happening.
Okay. Yeah. Okay. Okay, I will go back. For example, here, it's a good point. Don't want you to confuse a lot on this thing, but I will explain. What we have is, here we have discrete representations. We have a dictionary of words that are possibly entered to our system and to the output. So we have to construct a dictionary. But we want to represent them in a continuous way, in a vector. So what we build here is what is called an embedding matrix, which is a matrix where we have in one dimension the size of our dictionary, so all the words that we can process in our network, And then in the other one, we have the embedding dimension that we choose. So the number of dimensions in which we want to represent our words. And this is something that is trained at the end. So, but yeah, that's the way how we transform these discrete representations, which are words in a dictionary, to continuous representations that we can feed a neural network. And regarding the output, what we would have is then a linear projection that projects from these vector representations to the size of the dictionary. And we apply a softmax, and then we try to, it's like if it was image classification, but at its time step and through a lot of words in the dictionary. Yeah, that's more or less. Yeah. But it's good to us because at the end this will be the same exactly in the transformer. Any more questions till this point? Okay, so I move on to the attention mechanism. So you mainly already saw the intuition of the attention mechanism. So these ideas that we were saying now about connecting directly from the decoding steps to specific regions of the input, it's what attention mechanism is doing. Basically, the idea is that we can solve the bottleneck problem. So what we had before, this thing of collapsing all the information in a single vector, is what we call the bottleneck problem of the sequence-to-sequence, vanilla sequence-to-sequence model. And the thing now, the difference is that we can access all the encoder hidden states. So before, someone was asking, so I just keep the last one. Yeah, before we were just keeping the last one. Now we basically have access to all of them, to all the encoder hidden states. Okay, so somehow to the representations from all the input centers, and then attention will be able to select the most relevant parts. Okay, from the input, so directly connecting to the relevant parts in the input. So that's the difference now. We have the encoder RNN, but instead of just passing through to the decoder the last hidden state, now we pass. Okay, let's repeat again. So this is the first one, the second one, and the third one, but we pass all of them. Okay, so the decoder has available all of them. And we'll figure out somehow which are the more relevant ones to perform the decoding steps. Yeah, that's the idea, right? So the B network here, which is a decoder, can focus on different parts of the input. But again, let's do a parenthesis now for a moment, because I want to talk to you about the concept of query keys and values. Okay, this is something normally when the attention mechanism is explained, it's not necessary to explain the queries, keys, and values. But for today, I would like you to get used to these concepts now because they are super necessary to understand the transformer architecture. Okay, so imagine you have you have an information retrieval method where you, for example, I mean something really simple would be you have a folder with you have a photo library, okay, and you have extracted metadata for that photos, and you generate some tags. So you have a database of photos, all of them with some tags, and you want to search for a photo, searching for a word. Okay, so what you are doing here in this system, it's writing a query. Then the system compares this query with all the keys in the database, and the keys in this case would be the tags that you extracted offline of all the images. So then the system tries to match the query you launched with all the keys and find the one that match better your query. Once you find the ones that connect better with your query, then you will obtain the values, which are the images themselves. Okay, this is an analogy I use to explain the queries, keys, values. So you can see that the keys and values are really related. So are all the photos, which are the values, which the tags that you extracted at some point, these would be the keys. And you launch a query to search which are the keys that match better, and then obtain the values, which are the photos at the end. Everyone understand this analogy? Mm-hmm. Okay, so oops, it's not working now. Not the best moment to update the system. Now, yeah, so this is another example, another analogy for this. Imagine you have a bunch of folders, all of them with a key, and you are searching for you have a post-it with a query to search throughout the keys, and then at some point you will obtain the documents inside, which would be the values. And also I would like to give you this idea of this will end up being something called attention distribution. But for now, imagine that from all the keys you have here, you get a probability distribution telling you which are the keys that match better your query. Okay, so in this case, this one will be the one that matches better the query. But also this one, for example, is really related. Okay, so we are comparing queries and keys, getting an attention, a probability distribution, and then based on that, we will obtain the values. So how is this related to the attention mechanism? In our case, we will be working with vectors. So we will have a vector that gives a query, a bunch of key vectors, and a bunch of value vectors. Okay, and instead of just obtaining the one that is more related, what we will be doing at the end is doing a weighted sum of the values given this attention distribution that we just saw. We will see more in detail now. So how is this applied here? Okay, we close the parentheses now. We more or less know the idea of query keys and values. How is this related to applying the attention mechanism? We are in the same example than before. So again, we have the encoder RNN. This is the representation that we were using before. And we have the start of tokens. Start of tokens. Start of sentence token, sorry. And we want to generate the first word, like we were doing before. But before with this word was enough. So with the representation we get from here, we could generate the first word. But what we will be doing now is applying this vector here as a query, and all these ones, because now we have all of them available, not just the last one. We have all of them available. So we apply them as keys. So we compare our query with all the keys we have in the encoder hidden states. Some parentheses here. You will see that these values, which will act as keys or values depending on the moment, but they are the same vectors. This is why this is normally explained this way when you learn about attention mechanism. But yeah, I want to understand this concept that this can act as keys or values depending on the moment, because then later in the transformer, it will be different. So what we do is comparing the query with all the keys. So what we have here is what it's called the attention scores. And okay, I could explain you about different kinds of attention scores that are used in the attention mechanism, but I don't want to distract you. Mainly what we will do with the transformer is a dot product. So we'll basically do a dot product of the query and each of these keys. And then the result of this dot product, I pass it through a softmax, and then I can get this attention distribution. So remember,
these inquiries have all the same size, right? Because of this recurrent structure of the
Yeah, exactly. They are all vectors of the same size. So this is this intuition we were seeing before in the analogy with the folders, right? We now have a way. So what do you think will end up happening now with this attention distribution that we have here? Any idea? What will we do?
Keywords that introduce the meaning.
Yeah, exactly. So the network somehow learned that this is the key, that it's more related to the query. So this is where the most relevant information lays. So to generate the first word, the more relevant information now, the network has figured out that it's here. So what I do is now I use, as I was telling you, these vectors here, these hidden states, now they act as values, okay? They are the same, but now we understand them as values. And what we do is do the weighted sum I mentioned before. So applying this attention distribution, I get the final vector that it's weighted depending on this attention distribution. So this collapses information of all the sentence, but weighted on what the network has found that it's more relevant for the current time step. Okay. In this case, we are trying to generate the first word, which is he, and obviously the information relevant to generate he is il in French. Okay. Going back to what we had before the information from il should have traveled through all this RNN till this point. Okay, and this may be even a longer sentence, obviously. Now we are directly accessing to this information thanks to this weighted sum that we do here. So here we have a direct access to the information we have here. So then what we can do is use this hidden state and this context vector. This is sometimes understood as context vector to generate the first word. Any question? Yeah. Sorry? Oh, no, the query is basically the hidden representation that we have here in the decoder. So in the first time step in the decoder, I should go way back. So we have an RNN here, right? And we input the start of sentence token representation, and we input the hidden state, the last hidden state coming from the encoder. And with this, imagine a vanilla RNN, remember that W matrix and U matrix, you get an output for that layer. So this is the query, this output of the recurrent layer. This vector can be compared with all the keys, which are the hidden states in the encoder. And then this way we obtain the attention distribution. Okay, this is the case for RNNs. We will see that later in the transformer, this is different. Okay.
And you said that you concatenate basically the query and the attention output.
There is a slide later that will be more clear, but yeah, we concatenate it and we do a projection with an intermediate layer.
All right.
To do the
you have another neural network there.
Yeah.
Right.
Yeah. So this mixes information coming from here and from here. So this can be so this is done iteratively through the generation of the output sentence. So here I generated the word he, and now I can feed the word he to the input. I'm simplifying it here, so there are more complex ways to do this. This is what it's called greedy decoding, but it's fine for today. Okay. So the first word I generated, I put it to the input, and then I have the same. So in this decoder RNN, now I process the hidden state that I had before, the new representation that I had at the input, and this recurrent neural network now generates a new hidden state. So this hidden state is now the new query I have, and I do the same process that I did before. So I compare this query with all the keys. Now I get another attention distribution because after he, I want to generate heat. So the network learns to understand that the most important information now is in enter 10 and a bit. Okay, so it will average the values following this attention distribution. Me, in this case, the information for me comes from the M apostrophe and so on. So you see that now we have a mechanism thanks to this. Yeah.
So doesn't this depend on how we respond to the different words? Because this is related to the distance between related words. So if we have an encoding that is like related words have less distance with each other.
Okay. Yeah. Good question. So yeah, this is related on how we represent words, and yes, at the end, similar words have similar representation in this vector space. But at the end, what I want you to understand, and this needs to be applied to understand the transformer. Now we are talking about, the important information to generate me comes from this and whatever. But it's important to understand that this is not something that we choose or we force the network to learn these patterns. We are training this end-to-end. So we have parallel data with sentences in source language and sentences in target language. And the network just figures out how to do it. So the network learns everything, learns how to do this recurrence, how to keep recurrent information through the encoder and the decoder. And then this will affect also on how the query and keys are computed. because at the end, the representations are trained with this end-to-end manner. Also, the input representation, so these embeddings that we were saying before, the way we represent words, is something that we normally don't choose beforehand. We just start randomly, and then the network with backpropagation just trains these embeddings and ends up probably representing similar words in a similar way. But just for, I mean, because the network has solved this way the data set.
So the networks, the network doesn't learn the encoding, but the way
What do you mean?
it also learn how to encode words or no.
The embedding is done separately.
The ways.
It can be trained also.
Also.
Yeah, in the transformer, in the case of the transformer especially, this is something that is trained with the network. Yeah. But there are techniques to train offline word embeddings. That's true. But I mean, nowadays with the transformer, you just train also the word representations.
Gerard, sorry, just to double check my understanding is correct. In the previous example, you were translating from English to French.
Yeah.
While here is from French to English, right?
Yeah.
All right. So
It's just, I mean, these are the slides from Christopher Manning from Stanford.
that's fine.
So it's
It
just
was
an example that I.
to be sure that I was
Sorry.
getting the right meaning of this. Correct. Fine.
Yeah.
Doesn't this have scalability issues? Because the longer the sequence, you will have to learn so much more products and stuff. You have to keep all this information, say somehow, I don't know, that's important.
Good question.
I mean, you have to keep all the hidden states stored somehow.
Yeah.
And sometimes even, I don't know, I think in a book, maybe you make references on chapters behind. So.
Totally. To be honest, I've never applied this in a super long sequence, so I never thought about it. But yeah, you're totally right. Before we just had a single representation, which is super easy to fit a decoder. Now, if the sentence is super long, we have a lot of vectors there, and these operations are way more difficult.
Sorry, that's not clear to me. I thought that you could apply this approach for also single sentences, even within a book, right? You don't try to translate the book in one shot.
It depends on the task. So we are focusing on machine translation for this encoder-decoder structure or sequence to sequence, because this is how it's easy to understand first the transformer. But in general, RNNs can be used without the sequence to sequence architecture. So, but it depends on the task you want to train. I mean,
So
what do you want to do with
you can also translate a full chapter of a book as, I mean, one single input, series of inputs to your network.
But then what you will do probably is to split the book in chunks and then translate chunk by chunk.
That's another interesting aspect. Right?
But it's also true that yeah, we can. I mean, I'm talking about sequence to sequence and about machine translation, but for example, a topic that we will talk about today is language modeling. It's this task of predicting the next word in a sentence. This can be done without parallel data. So you have a book, you have tons of books, and you train the network to just, learn how to predict the next word, and this way you can generate synthetic text. You can do this with a single RNN. You don't need this encoder-decoder architecture. With just one, you get these representations and then predict that the outputs. This would be like what we do in the decoder, but without any conditioning coming from the encoder, just the decoder predicting the next words. So in this case, hit generates me, and then I will put it here. So imagine this without any connection to an encoder, just we predict the next word.
Still using the attention.
In the case of the transformer, yes.
Okay.
In the case of an LSTM, no. It will be just an LSTM storing information in the long-term memory and predicting next words. There are some questions. I think he was first. Sorry.
I'm not sure. Maybe you will talk about it later, but I was surprised to hear that you are actually considering this question about scalability, because I thought that with GPT-3 and stuff, we just forgot about scalability altogether and just said, okay, we have enormous resources and memory, and I thought scalability was forgotten long time ago. I don't know.
This is super interesting because this this intuition that he had will end up with a huge problem the transformer has that I was not I was not expecting to talk about it today, but remember me to talk about the quadratic complexity of the transformer, because we will apply something called self-attention that we'll see later. And this, I mean, what we are seeing here with this, all these encoder hidden states that need to be stored and then computing the query key matching will be a problem in self-attention. And I will mention it later. Remind me. So there was a question there? Yeah.
So can we say that basically we are learning the attention distribution?
Yeah.
And how this distribution evolves in time?
How this distribution evolves in time?
Yeah, I mean,
We do the sequence of the different.
Yeah. So
Actually, maybe if you use the attention distribution, you can understand the relation among the different parts of the sequence, and maybe the scalability can be handled somehow with this information you have. I don't know if this is.
I mean, yeah, but that's one way. I just want to understand if it's like learning how the distribution evolves in time.
Yeah.
So, for example, Riga, how the distribution Riga. But then depends also on the time window you're considering, right? So how many words you have?
If you include, I don't know, very long sequence,
Yeah.
and then you can understand more or less, for example, seasonalities, if it's a time series,
Yeah,
something like this.
So then in that case,
Don't know.
it really depends on the window. Because if you have a long
Yeah.
window, you end up with another distribution.
But if you want to study this and you put a very long window, I don't know,
Yeah.
then you can study and then back again to real implementation of this guy. Just guessing,
sorry, what do you mean by window here? Because I haven't.
Because,
said
for example,
anything.
if you have now you have a sequence, no? So
Yeah.
you have a sentence and you have a number of words.
Mhm.
Instead, you can have a different type of sequence, which is a time series, which is actually infinite.
Mhm.
So in this case, you have to window your RNN for a given length.
Yeah.
And then you, I don't know, shift one step ahead every time.
I mean, super interesting discussion. We should find a way to apply this, what you're saying, in a sequence to sequence. Because if you just have a really long sequence, I don't know how to understand this attention mechanism here now.
Yeah. Just intuition.
So yeah, I mean, you have this intuition that we could restrict this attention distribution here to just focus on a window. So we could, okay, let's be totally honest with it. So we could restrict this to don't be able to focus on all the keys available at the input for scalability issues and so on. So there are some particular kinds of attention that I didn't want to talk about today. It's that you can do this local attentions mechanism where you just focus on some windows. So that's why I asked, because I was surprised that you were talking about windows. You can do it. It may be probably easier to talk about it with a transformer, about local windows. Remind me also to talk about it. I have to. So quadratic complexity and local windows. Okay. Because I think it will be easier. Also, I want to be sure that you fully understand this. So when we feed new words to predict the next word in the sequence, the attention distribution evolves because the representation we are using now as a query is different. So somehow this recurrent neural network we have here, it's learning how to generate queries that solve this task of alignment. So learn how to work fine with the keys to be able to learn this attention distribution. So this is how this is evolving in time, because this is a recurrent neural network and this is changing the query every time. This, I think it's something important to have here. Okay, and later we can talk about local attention. So again, another representation for this, we have all the encoder hidden states and the current decoding hidden state that we have now in this and a specific time step in the decoding. We compute the scores with a dot product, and we apply a softmax, and this is the attention distribution. We have to wait. The problem with ifs in presentations. Okay, we get the softmax, and then what we do is we do the weighting of the values, and then we sum them, and this is the context representation that we said before. Okay, representing in an informed way the important parts of the input. More GIFs, more animations, the hidden state. So here we have what we were saying before. We have a hidden state at the input in this recurrent cell and the input. Okay, and this computes a new hidden state that we use to compute the similarity with this to get a context vector. And this is what we were mentioning. This concatenation here with a linear projection and another linear projection to generate the output word. This is how we could do this attention mechanism for a sequence-to-sequence task. And this leads us to, so a nice thing about applying attention is that we can clearly see this alignment between words that the network has learned. So for example, with this input sentence, we have here the agreement on the European Economic Area was signed in August 1992. This is the example that we saw before. We generated these outputs, and these are the attention distributions for each decoding step that we learned. So in this case, this first row here is the attention distribution that was used to generate the word L, and so on. Okay, so for example, the example that we were saying before, the case of generating European, remember that was the first motivation that we had. Now the network has learned to generate this attention distribution where the main focus is in European. Okay, and maybe then there are other words that need a mix of information from the input. So ET is speaking information from was and from signed. For some reason, the network needs this information. And I have a small question here. So at some point we apply a softmax, and I wanted to ask you, in which dimension does this softmax been applied? In columns or in rows? In rows, exactly. It's applied in rows. Okay. Why? Because this is what I told you, right? This is the decoding step. So the decoder is generating this word and needs to focus on the encoder hidden states representing all these words. So these are each of the queries. So we are now using this query, and these are all the keys available. So I computed a score between the hidden state representing ET and the hidden states representing all these words. After the scoring, I apply a softmax in this direction. Okay. So applying a softmax in this direction means that if I sum the probabilities I have here, I sum 1 if I sum in this dimension. Questions till this point? So how did this affect the neural machine translation field? Maybe the naming they use here is not so clear now. These two here are the ones using attention. Okay, so the two using attention are this line here and this line here. Okay, and as you can see, okay, sorry, the axis. We are measuring BLEO here, which is a score that we use in machine translation. Like we can use accuracy. For machine translation, we use BLEO score. We can use other metrics. This is the most famous one. And what we are doing here is measuring the BLEO score for different lengths of sentences. Okay. In general, for all sentence lengths, what we see is that attention in general performs better than the other two options. These two here. Okay. And you may be wondering why we have these 50 ones here and these 30. So this is the maximum. This comes from the first paper that proposed attention for neural machine translation, and this is an example of results they gave. And basically, what they are doing here is training the network with sentences up to 30 words or up to 50 words. Okay, so if we compare directly, like the two networks with attention and without attention with the 50 words, we can clearly see the difference. So while this one, so this is the one trained with sentences up to 50 words without attention, and this one is the one with attention. Okay, so we can clearly see that when the sentence is longer, remember that problem we had with the bottleneck. If we have a longer sentence, then it's way more difficult for the network without attention to collect all this information with a sentence of 50 words, for example, while the one with attention maintains the performance.
But Gerard, sorry, doesn't the size of the feature vector that you consider have any impact on the performance of the?
Yeah, you're totally right.
It's a bit unfair, right? Because when you use attention, you are adding another dimension of features to infer the next term. While with standard RNN, you just use the feature generated by the RNN.
Super interesting question, because there are some recent works. I mean, this is not something super conclusive yet, but yeah, maybe just adding a higher embedding dimension allows you to store more information. Maybe we could go back to the vanilla sequence to sequence. Yeah, I was really impressed by a work from a guy from Meta AI that did some research on this by going back to the vanilla sequence to sequence, by adding a higher dimension in the representation and also forcing it to, well, be difficult now. But yeah, at some point we may go back to this idea.
Just increasing the size of it and that's it, or adding some criterion to filter the propagation of the information from time to time.
Super nice discussion.
I'm just happy that my question was not a stupid one. So
no, I mean, yeah, it makes sense. You are giving more capacity to the network to store more information with more dimensions. I could talk about that paper, but the thing here is like, okay, the difference with attention is that we are not adding more dimensions. Like, we are giving the possibility of direct access of information coming from different points at the encoder. Let's say this way. I mean, it's quite different. And this is the moment where I explain a bit. So,
Do you want me to?
yeah, maybe, yeah. Oh, this is function. Okay, for that.
Yeah, no worries.
Okay. So there's like propagation. Nice. So, what we have, okay, classical. So we have
the green one used to be.
it's always like that, right?
I had one.
The red one.
I'm going to ask some new.
Okay, we will do it.
It's better.
Yeah, we had the hint here. It was written. We have this example. Je suis. We fit this here. So what we had before, imagine this representation is of this size. Let's put it in size 4. And before we were using just the representation to go to the decoder. With attention, we have access to this. And attention can pick where is the more relevant information. And what you are proposing would be doing this. Just wanted to clarify that everyone was following the discussion. So it seems that this way, the network can keep more information, right? But if you see, we are giving more capacity to the network. Okay. Thanks. So yeah, we are giving the possibility of storing more information here, but there is no any. So there is a concept that I like regarding neural networks in general, which are inductive biases, which are things that we assume a bit in networks to make them easily learn something. And I think that the attention mechanism is a good inductive bias, because when you want to generate a word, I mean, you can, it's the motivation that we were seeing before. You can clearly pick where is the relevant information in the encoder, and attention mechanism allows you. This mechanism that we just figured out by just adding more dimensions can store that information, but we don't have this inductive bias where we can directly design the network in a way that it can pick information from specific regions. We have to let the network figure out this through the dimensions.
I mean, there is also another thing that I have learned. Whenever you're designing an outbound encoder, you want to limit the capacity somehow, because you see that if you give too much capacity, too big, the vector is too big, and the content vector. It will be less capable of really extracting the good features. It will be extracting maybe previous features. So a way to make it extract the real manifold where your data is, with the real structure of the data, is to constrain the capacity. You do it by the side, you can do it in a different way with the noise, you can do it with I don't know, like a prior, which is like parts, different ways of doing it. So I'm afraid that if you give it too much capacity, it will not be as efficient. Representing it with a limited time.
And so,
So it's not trivial.
so I'm aware of this. I was just wondering whether you ever made the comparison, right? With the same, I mean, a fair comparison.
Fair comparison will be nice.
Yeah.
With the same final size. So you see, in a case I have a matrix, like 1, 2, and 3. The other
Exactly.
case I have a vector. Which
12
is like,
here in the example that we have.
exactly.
Yeah, totally.
All right, thank you.
Really
Very interesting.
next paper.
And I have another question actually
Yeah.
regarding the figures that you were showing us with the performance cars. So next slide, I believe.
This one?
All right, just to have a benchmark, what would be the view score for a human translator?
It is a linguistic score.
That's right.
That is telling you how much the sentence that you are.
Yeah, I know, but I was wondering what the target. What would be a perfect translation?
In reality, this is a percentage, so the perfect score will be 100, but you never get 100, because the idea is that in translation you cannot find perfection, because maybe
It's a matter of also interpretation, I guess. Right?
exactly. So this blue score, what does is well, it computes the number of n grams that coincide. So 1 grams, 2 grams, 3 grams, 4 grams, which are like a 3 gram would be a 3 gram, would be a pack of 3 words that coincide between the reference and the one that you obtain. And this way, it's the way in translation we measure the performance. A performance that of a good machine translation system would be like between 30 and 40.
Right.
I mean, the systems that we have nowadays are around these scores.
All right, perfect. Thank you.
This was some years ago with the transformer and everything went crazy. These scores, but this is quite good translations already.
One question.
Yeah.
Just to be sure, in the end, did they give us the right to the RNN certificate or?
That's a question I also have, and I think they were not totally fair by cutting it here, because the other thing that I didn't want to mention to don't confuse you is that the RNN with attention trained with 30 words maximum. It's this one here, and this has a drop also. This one seems totally flat, but because the 50 is here, maybe we will see a drop also here.
Yeah, but the 31, the drop before the 35.
Yeah, that's weird. Also, that's weird to me too. I don't know. This is the figure they showed. The important thing here is to see that in the I mean, in general, we prefer to train with longer sentences because then the network will be used to see longer sentences. And with the 51s, we can clearly see the difference. There is a huge gap, especially, I mean, there is a more than 5 bleu here, and there is a 10% bleu here in sentences with 40 words. This is a lot. Something else? Because now we are arriving to the transformer architecture.
Okay.
What time did you start?
9:40, so it's 1 hour and 10. So
It's a good moment for a break?
yeah, maybe yes.
Okay.
Yeah, sure, one. So, yeah, 5-10 minutes maybe.
Yeah.
Okay.
Sorry, where was I? The transformer architecture. Okay. Yeah.
Can I ask a quick question?
Yeah.
How do you train the previous model?
The previous?
How do you train the previous model? You use backpropagation of the time?
Yeah.
Okay.
Yeah. Okay. I think at this point you have enough background to start learning about the transformer architecture. So when we open the transformer paper, these are the 3 most famous figures that we find with the paper. So this is the one we saw before. This is the whole transformer architecture. Then we have some blocks here that are this multi-head attention that we'll discuss later, which can be represented with this diagram and also with this equation that we have here. And this scale.product attention we have here. I mean, we already talked about dot product at some point, right? Well, you have some hints there. So this can be represented with this block diagram we have here and this equation. But the most important point here is this. What I'm saying here, the transformer removes the recurrence mechanism thanks to self-attention. And these 2 blocks we have here are the ones representing self-attention. So what does it mean? Before, we were basing our processing of the sequence on recurrence, on these recurrent neural networks that today we've learned about them, where we were reading word by word, right? But now we remove this idea. Okay, so forget about it for now. We now base all the processing of the sequence in this new concept, which is called self-attention. And obviously is related to what we've just learned about attention, okay? So this is a change of paradigm on the way of processing the sequence now. Okay, so what I will do now is to base my explanations on this figure, and we will start depicting which are the blocks that we see here and explaining what we see. First, I don't have here in the slide, but maybe not obvious. What we have here is the encoder part, and what we have here is the decoder part. Okay, when you see next time this figure, now at least you know you have an encoder and a decoder. Encoder architecture, as we just saw, processing sequence to sequence task. We also have this n times here. This is because what we have here is not the whole encoder. It's just an encoder layer that we can repeat as many times as we want. So we can stack many transformer encoder layers. I think this is an error from the original paper that they use the same letter for this, because it seems that it has to have the same number of layers in both the encoder and the decoder, but it's not. Actually, you can, depending on the task you're training, you can make it asymmetric. So yeah, you stack n encoder layers and let's say n decoder layers, which are these blocks that we have here. So I told you before that these 2 blocks that we have here, it's something that we call self-attention, but then we have another attention block here, which is what we call cross-attention. I want to give you some hints to try to figure out what is happening here. And if you see in these 2 blocks here, the blue ones, we have 3 arrows coming in. And in this one, which is the one that I call cross attention, we have 2 arrows coming from the encoder and one arrow coming from the decoder. So first, what we've learned today that are three things that go together. Any idea? Some of the concepts that we saw? A pack of three things that always go together. Exactly. Queries, keys, and values. That's why I insisted on showing you about queries, keys, and values during the attention mechanism. And so the ones that I'm telling you that it's self-attention, the three arrows, the queries, keys, and values, come from the same input. And the one that I'm telling you that it's cross-attention, there are two arrows coming from the encoder and one arrow coming from the decoder. Does this remind you to something that we saw before? So the two arrows coming from the encoder are the keys and the values, as the ones we had before. And the ones coming from the decoder is the one coming from the query. So in this schema that we had before, remember that we were using these encoder hidden states as keys and the values. And the current hidden state here was the query. So in these three arrows that we have here, the one coming from the decoder itself is the query. And the two coming from the encoder output are the keys and the values. Yeah.
Are they still the same? Values?
No. That's why I insisted before that we needed to understand them differently, because now they won't be the same. You will see how they work. But in general, these are something that you extract from the encoder, where you have all the hidden states that we had before available. So this is basically the same that we had before. This cross-attention, some differences. There is something here telling us that it's multi-head that we still have to learn. But the idea of what it's doing, this block here, is the same that it's doing before. So we are introducing information coming from the encoder in a wise way in order to pick relevant information depending on each time step in the decoder. So to generate each word, to pick the relevant information coming from the encoder. That's what it's doing, this purple block here, okay? But then we have self-attention, that it's something new that we have to learn now. And before starting on how we compute this, telling you on how we compute this, I want you to give some intuition. What's the idea behind self-attention? Remember that this is a different way of thinking. We don't have recurrence anymore. We have self-attention. And the idea is that now we have an attention that allows words to attend to other words in the same sentence. So now let's put an example. We have this sentence. The animal didn't cross the street because it was too tired. Okay. And we are analyzing the self-attention in the word it. Okay. So what we are learning here is, self-attention is able to capture information from other words, also itself, but from words in the sentence in general, to improve the representation. I like this example a lot because this is a case of a pronoun that it's referring to some noun, right? And we have two candidates of being the one that it's referring to. So we have animal and we have street, and it could be referring to both of them theoretically. But in this case, the network is So we are at the input, okay? And imagine what I told you before, that for each word, we have a way to represent it as a vector. If we have the representation of the word it by itself, it has no meaning. What does the word it means without any context? So what we are doing with self-attention is contextualizing words. So if I put it in this sentence and I use self-attention to get that contextualized representation, the representation I get for the word it is contextualized in this sentence. So what self-attention can learn, for example, is understanding that this element of the sequence is referring to an animal. Because thanks to self-attention, we learned that the relevant information for it is here. In this case, this self-attention is actually giving more importance to animal than street. So it's understanding this self-attention mechanism that it is referring to the animal. This is like the general concept behind self-attention. Is this clear enough?
Yeah, that's clear, but it's not clear to me how you can frame such a thing.
This is something that we have to remind constantly in this session, that this is crazy how neural networks are trained nowadays. At the end, we just train them end to end. So in that machine translation case, this is something the network figures out. We're just giving the network the possibility to do that. So the network will learn to do this if it finds necessary to solve the task that you're training it for. So
therefore, this self-attention, let's say, block is inside the whole architecture, and
yeah,
and it learns by translating from one language to another one.
Yeah,
it learns these inner relations between the systems.
Yeah,
okay.
We'll see later that it's not always so interpretable as this case. In this case, it's so clear because we can clearly see that it's picking information from the animal.
Sure.
Not always like this.
That's clear, right? Fine.
What the network is learning in the end is the representation of these words and the state of these words. When you do the product and you compare them, you're learning how to represent this, right?
Good question. For now, I just wanted to give you the general idea. Later, we will see what we are exactly. I think it's the following slides. What we are exactly learning. But in general, the concept is this. Okay, I want to learn something that allows it to be contextualized in this sentence and then improve its representation. And the example is that it by itself has no meaning from the beginning, but if I put it in this sentence, then I can improve the representation and give more information to it, to the representation of it. Is this clear? This is the concept behind attention, self-attention. So the idea is that, remember, we removed recurrence. We are not processing recurrence. We are basically doing this for all the words in the sentence. So we are improving representations of each word by contextualizing them with self-attention. So here in the output, we will have an improved representation of animal that maybe the network has learned that has to pick information from target to improve the representation of animal and also adding the information that this animal is target. Okay, but this is something that we don't supervise, but the network can learn to do. So all this is done with this operation, the scale.product, especially the scale.product by itself, it's done here. So we have queries and keys. Remember what we were doing before. We do a matrix multiplication. Later, I will give more details on this, but basically what is happening here is this dot product. And then we have to scale it. This is some details that I introduced in the transformer paper. Before, the dot product attention was done without this scaling. This is scaling with the square root of the dimension of the keys, but not super important now, okay? Just, yeah. So we have this sequence. These are vectors representing words at the input, okay? And we want these outputs, which are the contextualized representations of these words in this sentence. Okay, we can think about words or we can think about any sequence that we are processing. We are in the machine translation case now. But wait a moment before giving you more hints. From this figure here, which I told you that it's everything that is happening, I remember the first time that someone explained me about the transformer. I was like, okay, I have some matrices here that are, well, some representations here, which are the inputs, like queries, keys, and values. And what I do here, there is nothing that is learned. So at the end, I'm doing a matrix multiplication of queries and keys, but nothing is learned here. Scaling operation, this masking optional, I will give more details later. A softmax, and then a matrix multiplication again. There is nothing that is learned here. What is the trick? What's happening here? It was not clear for me at the beginning. So the trick is that we have this, and this answers your question. So what we have is a projection that generates queries, another projection that generates keys, and another projection that generates values. And by a projection, I mean a linear layer, perceptrons layer, okay? This is a matrix multiplication at the end. But these are the weights that are learned in this self-attention module. So what I'm doing here is, for each word in the input, I generate a triplet of queries, keys, and values, okay? So yeah, these projections are learning a way to generate a new representation for each word that act as a query, as a key, or as a value. And then what's what I do here? So I will use, for example, the query in the first word, and this is the same thing that we saw before. And we have all the keys that we just computed. So we can do the dot product, apply the softmax, and then we get the attention score. And now we have an attention score of this query contextualized with all the words in the sentence. Okay. So this is the distribution of that distribution that we had before. Remember, the one picking relevant parts from the encoder. Now we have in the same sentence, in the same sequence. So in this case, it's the most information comes from the third word to contextualize the first word. Okay. And once we have these scores, what we do is doing the weighting of the values as we were doing before, and doing the sum. So a weighted sum of the values considering these scores. And what we have here is the contextual representation of this vector here, or this word, contextualized in this sentence. Thanks to, remember, these projections that I learned. So thanks that I'm learning how to generate queries, keys, and values from each word in the sentence. Okay? And here is the trick. And this is not obvious. Probably this is the most tricky part of the self-attention thing. And understanding that what we are doing is generating triplets of queries, keys, and values that will do the job later. So the network is learning how to generate good query key representations to make the relevant parts of the sentence to match in this query key dot product. Yeah.
What's the difference between autocorrelation and self-attention?
Wow, was not expecting this question.
Yeah. Now it's like I don't know, but it seems like it's kind of autocorrelation. So you have a vector, you find the stick with the correlation. Using the learning. Yeah. Attention again. The meaning of the self-attention distribution is kind of an indicator of how one single word is correlated to one component of my vector is correlated with all the other components of my vector. Makes sense?
Maybe there is no time shift because in autocorrelation you always relate the past to determine the new.
Yeah.
Here I don't know.
If you consider a sentence as a set of words, and words, you have the first word that times one, second word that times two. So in this case, you have each, for example, and you try to find the correlation with all the other different time instances. The meaning.
It is
I'm
indeed.
talking about the meaning, not the process.
It is a correlation measure, but performed on the feature vector rather than on the original. Right.
Yeah, the trick here is that you learn how to generate these queries.
Weights are different. W.
Exactly. And in the sense that I was telling before that it was not obvious to me to understand what is learned in this. I was thinking like everything was happening here, and maybe this is somehow related to your question, because our intuition would be that if we do this scale dot product, the highest relation would be with itself, and this is not always like this. In this example we have here, the most contribution comes from the third word to the first word, and this is just because the network learned to project these input vectors in a way that they generate these queries and keys that maybe match different stuff.
Yeah.
So the trick, probably the answer to your question is that it's these projections here.
So just to
recap.
The same input, the green part, goes through WQ, WK, WV.
Yeah.
Independently, these three projections are the V, T, and Q vectors that are on top.
Yeah.
So what we're doing, probably, but correct me if I'm wrong, with this machinery that we have in between, we are forcing the backpropagation to learn good ways there. And we have a perfect representation that will be meaningful to express a probability distribution.
That's perfect description of what is happening. I don't know if everyone heard it. But yeah, the summary is that through backpropagations we are learning these projections that will end up working in a good way to do this, to learn this attention distribution, to generate good representations, to be able to do meaningful, you were saying meaningful attention distribution. Yeah. Sorry, I don't know if you were the first.
Thank you.
Yeah.
The queries keys and values, they're always the same for the same input, for the same representation, right? Same keys.
For the same X, so if you have, what do you mean?
The keys, values, and once they are learned, doesn't depend on the context. It doesn't depend on the.
No, exactly. These are applied. I think he mentioned it. So we apply them all for all the inputs. Yeah. Same projection. Yeah.
So this technique is applied for self-attention in general, applied to any domain, or just for the word embedding.
When you read about self-attention, that's what it's happening. You have a sequence, you project all the sequence with the same projection to generate queries, keys, and values, and then apply this scale dot product, and you get the contextualized outputs. Yeah. I think that's your problem.
We're still using the same weights for all the words in this, so because I thought that was a problem that in RNNs we have the same weights, and when we backpropagate, it's a long backpropagation. Isn't it the same thing? Everybody the same thing?
Not exactly, because the problem, and I think it was him that mentioned before, is that when you share in an RNN, you have this shared matrix. If you have a very long sequence, that leads you a problem with the gradients, and you end up with vanishing gradients and some sort of problems. Here, you're not backpropagating through time, so you don't pass multiple times through this through these projections. We'll see later, but we basically do this projection in parallel for the whole sequence at a time. So it's not the same because we don't pass multiple times through the same matrix.
So just to understand that X1, X2, and X3 are sequences or words?
Words, sorry. Vector representing words.
And independently for each word you're applying this.
Yeah, I mean, the same projections are generating the queries, keys, and values for all the sequence at a time. We'll better see later how it parallelizes.
Okay.
So another point of view of the same operation, we have here a sentence that we will see some examples later. This is from, by the way, if you want to learn more about the transformer, there are some things that today maybe are not super clear. I recommend you to check this post from Jay Alamar, the illustrated transformer. This helped me a lot when I started learning about the transformer, and there are many fields that I use from that post because this is super clear. So we have this sentence, super short sentence in this case, just an example. It's saying thinking machines. Okay, there's not even a verb there. You have the embedding, which is the vector representing each of these words. And for each one, with these projections that we are learning, we generate a query vector and a key vector and a value vector. So what we do here is the dot product. Probably you don't see it, but you get a score for. I mean, in this case, we are analyzing just the first word. We are contextualizing just the first word. So this is the query for the first word with the key of the first word. The query of the first word with the key of the second word, because we are just working on the first word here. We get a value, we do the division by the scaling that I told you that, forget about it. And then we apply a softmax. And here, probably you don't see, but we have 0.88 and 0.12. These are the scores that we use to weight the values now, and we sum them and we get the final representation. And the idea here is that this representation is collapsing information, is a contextualized representation of thinking in this sentence, okay? Because it's using self-attention. Another views that may help you to clarify it. So we have these vectors here: walk, by, river, bank, and we generate the queries, we generate the keys, we generate the values. So we perform this dot product, actually a matrix multiplication between the queries and the keys, and we obtain this. That we do the scaling and the softmax, and we end up with something like this that we will multiply with the values to do the weighted sum. This is equivalent to the weighted sum. So I wanted to ask you if this reminds you something, what we see here.
Softmax is applied on column.
Softmax in this case is applied on column. But what I wanted to answer here is that this is the attention map that we had before. Remember when we were doing attention for sequence to sequence that we were saying, okay, it seems that to generate each word in the output, I can see where I have to focus. So in self-attention, we also have this. And the cool thing is that I can see how self-attention is mixing information, how it's contextualizing its representation. So in this case, the representation of the first word here, which will be the first column in this case, is picking some information also from the first word, but same amount from the second word. The second word is just picking information from the second word, and so on. You could analyze it. But the idea I want to give you here is that we can understand. And before, in the break, I was speaking with someone that back there, that we were talking about interpretability, that attention as a side effect allows us to have better explanations of how our models are processing stuff. And I want to contrast, like I told you that we dropped recurrence and we are now using self-attention. And this is also a good side effect from using self-attention, that before in recurrence, we have just a vector that we share a projection and we don't know how information is kept in that vector. Now we have self-attention, and with self-attention, we have these attention maps. And thanks to the attention maps, we can understand how the transformer is picking information, is mixing information from the inputs. Okay, so it's a good side effect and from the self-attention now. So it's not just the cross-attention in an encoder-decoder. So just the self-attention, someone was asking if I want to use self-attention, that's all? Yeah, that's all. If you want to use a self-attention module, you can interpret how it's learning to mix information from the inputs. Any questions?
We can discuss it.
Okay. It's almost time. Let me see. Yeah, I can end with self-attention. Yeah, so I was telling you about parallelization, okay? In the examples we had before, we were comparing every query with all the keys and then move to another query and all the keys. But that's not how it's happening, actually. The self-attention operation is fully parallelizable. First, starting with these projections, I think I mentioned before. So we have this super short sentence that we were seeing before, where we have two words, thinking machines, and we have a vector. So each row here is a vector representing each of these words. So first, when I generate the queries, keys, and values for each word, I can do it all the sequence at a time. I think that's something that we're saying, right? So if I have a super long sentence here with 100 words, I just have to multiply this huge matrix that I would have here with this projection, and then I would get the queries all at a time for all the words in a sentence. So first, we parallelize how to compute the queries, keys, and values. So just to make sure that it's clear, every row here, it's the query representation that I extracted with the projection of the first row and the second word, or the first word and the second word. Same for the keys. So I have the two representations for the words, and same for the values. And at the end, what we were doing before with the dot product and the scaling and the softmax and so on can be all applied with this operation of matrices. So what we have here, this matrix multiplication between queries and keys, it's basically what we see here. So the matrix multiplication of the queries matrix with all the sentence and the key matrix transposed. This will give me, if I apply the scaling and I apply the softmax, this gives me this matrix here. If you do the math, you will realize that you end up with sequence length times sequence length matrix. And then if you multiply this attention matrix with the values, you will end up with a weighted sum of the values depending on this attention matrix that we found. This is what would happen in this operation. So doing everything at a time, everything parallelized, we obtain the contextualized representations. The first one here is for thinking. The second one is for machines, all operated in parallel. Okay. And I also, before I said something that I wanted to talk about quadratic complexity.
Right? What you parallelize is what we have in the left here, the three multiplication.
This is parallelized, yeah, but then also the operations, because before, if you remember, here we are just computing the query key relations for the first query. So what we see here, and we were seeing before here, we're just contextualizing a single word with all the keys, but a single word, and then we get one output. But this is not done one word at a time. This is all done in parallel. So it's parallelizing this projection, this generation of queries, keys, and values, but also this operation here.
For everyone.
For everything at the same time. Okay, it's 30 minutes. I will end here. The think about the quadratic complexity I was saying before is that, and this is something that it was not intended to talk about today, but I think it's interesting. So we have a problem here of quadratic complexity, since I mean, if you do the math here, the number of operations that you have to do here to multiply the queries by the keys scales quadratically with the sequence length. Because at the end, you end up with a matrix of sequence length times sequence length. So this is a huge problem of the transformer. I just wanted to talk about the good things about the transformer today, but I will be totally honest, this is a limitation of the transformer. You cannot do self-attention, or not the transformer, in general, self-attention. You cannot do self-attention on really long sequences, because the matrix multiplication you will have to do here scales quadratically. The number of computations.
Q&K, they need to be the full matrix. This is what you're saying.
No, I mean,
Q&K, they scale with the size of the input, no?
No, not exactly. So the matrix multiplication, the number of operations that it's doing, it's 4 times every time I duplicate the sequence length. So if I have 2 words here, I have to do X operations. If I have 4 words at the input, which is doubling it, I have to do 4X operations. So it's a problem.
At the end of the day, you have to compute the self-attention for every pair of the input, right? So you have a square matrix.
Yeah, exactly. But that's a limitation. Okay, so at some point with really long sequences, you have problems of.
And the matrix is not symmetric, right? So the self-attention of word 1 with word 2 is not the same as word 2 with word 1.
No, because you computed differently the queries and the keys.
And query and key.
Exactly.
This is the quadratic complexity.
Okay. So I don't know why before we talked about this. I think, it was someone pointed out that if this storing of the whole encoder hidden states could be a problem. This is especially a problem here, not exactly encoder hidden states, but this idea of, if attention is this idea of picking from the whole possibilities, picking what is the relevant parts. If it's a very long sequence, especially in self-attention, we have problems with this quadratic complexity. And I will have here. So I talked about quadratic complexity that is related to something that someone pointed out before. I think we can stop.
All right.
We continue in the afternoon. Okay, there are some questions.
How do you manage the variable and the input matrix at the end of value? There's for each sentence that you get, the size of this matrix is different.
Yeah.
And then you have to input it to the decoder, right? You give this matrix to the decoder.
So first, we are in self-attention, and the thing here is that we are projecting all of them, queries, keys, and values, to the same embedding dimension. In this case, we are modifying it, so we have vectors of size 4 in the input, and we transform them to size 3. When we do the matrix multiplication between the queries and the keys, we are operating in this dimension, and we end up, in this case, we will end up with a matrix of 2 times 2.
Yeah, but at the
Here.
end, the rows depends on the length of the sentence, the range of the matrix.
I can maybe write it.
With the number of words, we have another row.
We have how does it work to move it up? Possibly? No. So the queries, we put it in proper mathematical notation. These are T, which could be the sequence length, times E, which is the embedding dimension. So this dimension that we choose to represent it. And this also is for the keys, and also for the values. Okay. When we are doing queries, the multiplication between the queries and the keys, we have a matrix of T times E multiplied by the transposed one, which is E times T. This ends up with the representation that we were saying before. So here you have, when you have the attention weights, you have T times T. This is the representation we're seeing here. This is the T times T. So if the sequence length varies, there is no problem here. Because this is not when we are operating in the queries keys. Then this is multiplied by the values, and the values is a matrix of T times E. And we operate here. So you're right. I mean, in self-attention, we don't have any problem here because we can do this operation because the length, if it's different length, it can be operated. But then, for example, in cross attention, we are also applying this. And there is some restriction here that the keys and the values, so this comes from the keys and this comes from the values. The keys and the values need to have the same sequence length, while the queries can be different. But this at the end is what we are doing. So if you remember, when we are doing cross attention, in the original attention, the keys and the values both come from the encoder. So they have the same length. And it's the queries that can be different because the sequence you have at the output, at the decoder.
T of the queries one, which is constant for every length, right?
Sorry.
So the T that you meant here at the encoder Z matrix is the number of queries.
Yes. Yes. Yeah. Correct.
So, can you go to the previous,
This one?
yeah, so here for the learning phase, we learn the W, right?
Yeah.
So the W's are learned and are fixed when we want to use here.
Mhm.
So that's what I have the same question. Is the W size depends on the
Exactly. So the W size is on one side the input embedding dimension, and the other side is the output embedding dimension.
okay, so for test phase, for interior space, when we want to test with the various inputs, like for example, a 5-volt input, and we have a W, they have learned the W for how much input.
No, the thing here is that this dimension is fixed. This is the dimension the size of the embeddings that I choose to represent words.
Okay.
It's this here, the one that changes. This is the T, and this is the E.
So the
And here I have E in and E out.
okay, so the word embeddings are all the same length.
Yeah. These are all. This is word 1, word 2, word 3, word 4. All of them are of size 4. I can choose then later when I compute the queries, keys, and values to have a different size if I want, but they will be able to operate between them.
And here E is the size, is the length of the sequence.
No, sorry. This is the embedding dimension. So the dimension I choose to represent the queries, keys, and values.
And where does the length of the sequence appear?
So if here, what I explained you here, this T times E, it's what we have here. T is the two words that I have in the sentence. E is the size of the vector I choose to represent every word. So every word is represented as a query with a vector of size 3. And I have two words in the sequence. This is the T. Okay, so T dimension, E dimension. So yeah, basically, if you see that T dimension, I don't touch it when I do the projection. When I do that operation, I end up with a T times T here. I don't know if.
At the end, when this model receives different sizes, different sequences with different sizes, the size of model does change.
This one, yes, it does. But at the end, if you realize, once you did this operation, the T still is the same. So we have two words. This is the T, the sequence length. The output, we also have sequence length of 2. So I want to make this clear. What we have here, every row is a contextualized representation of the two words I had at the input in this sentence. This can be 10 words. I don't care. All the operations work anyway. The only problem with the sequence is that operation I told you here that scales quadratically. But the rest, I will have, it will simply change. Yeah, that's more or less what I want to do.
Can I give an example to see if I understood correctly the set attention? So in two sentences, for example, it is warm or it is a cat. So what we are doing actually here is we get different output for it in these two sentences.
Yeah.
So that's the whole.
Exactly.
Okay.
Exactly. The network has the possibility to change the representation of it to incorporate information of the exactly. Exactly. That's the main intuition of self-attention. We do it this way. Yeah.
In the end, all of this nothing goes into a Leo Scott or what?
Sorry.
The loss in the end of all.
No, it's a loss. Where you have the whole sequence, you are trying to always predict the next word.
We'll see it.
We'll see it later. Yeah, it's not the blade because you cannot backpropagate with the blade.